Assalamu alaikum, my name is Mohamed Munir and today we'll be covering lung mechanism 1. So a quick reminder before we get into the actual lecture, in physiology when measuring pressure, atmospheric pressure is usually set to 0. This simplifies the measurements that we take in the body. So for example, if you wanted to take the blood pressure of someone, you'd say that their blood pressure was 100. Now 100, well it's not actually 100, it's 860. But for the sake of simplicity, we just refer to it as 100. One exception to this is partial pressures, where this rule doesn't apply if you're measuring the pressure of, say, oxygen, carbon dioxide, or nitrogen. Here, actual barometric pressure is used, which is 760, to not confuse anyone. We'll be using these two examples to explain transmural pressure, but first let's define what even is transmural pressure. It is the difference between inside pressure and outside pressure, and as we're about to see, it is going to be the primary driving force in the change in volume in the balloon, so keep that in mind. Now, in the first example, we have a syringe connected to the balloon and it will be inserting air into the balloon. Now this will cause an increase in inside pressure. Now while outside pressure stays the same, there is going to be a positive change in the volume, so the balloon will expand outside. As for the second example, we have a syringe connected to a box around the balloon. Now this time we're going to be decreasing the pressure outside the balloon while the pressure inside the balloon stays the same. This will also cause a positive change in the volume of the balloon. Now in both scenarios, the volume of the balloon will be expanding outwards. Why? This is due to the positive transmural pressure difference that has been created in both examples. A fun fact is, for the first example, this is essentially how we conduct artificial ventilation. Meanwhile, for the second example, with decreasing the pressure outside the balloon, that is how our diaphragm helps us to breathe naturally. Okay, now let's talk about compliance and how we measure it. So, compliance is defined as the change in volume over the change in transmural pressure that causes the change in volume. Basically, what we refer to it as how easily something stretches. Now, if you look at this graph here, what can you notice? There is a part of the graph with a steep slope and a part of the graph with a much flatter slope. Now, what you notice in the steep slope is while the change in volume is the same all throughout, the change in pressure required for that change in volume increases over time. So in the steep part of the graph, you'll need a very small amount of pressure to cause a change in volume. This is what we refer to as high compliance, giving us a steep slope. It's very easy to stretch. Meanwhile, in the much steeper part of the graph, the amount of pressure needed to cause that exact same change in volume will be much higher, causing a much flatter slope. This is what we refer to as low compliance, meaning it is much harder to stretch. Okay, so we already established that the change in transmural pressure is the main driving force behind the change in volume. But let's apply this to the respiratory system. So the main pressures that we have are the alveolar pressure, which is found in the alveolar sacs, the pleural pressure, which is found between the lung and the chest wall, and we have the body surface pressure, also known as barometric pressure, which, as we established previously, is 0. And we're going to use these to find the compliance of the lung as well as the change in volume, as we're about to see. Okay, now to find the transmural pressure in the lung, we're going to have to subtract the alveolar pressure from the pleural pressure. So And just you'll have to visualize this as the lung. I mean, it's right in front of you, but yeah, subtract the alveolar pressure from the pleural pressure. Now, as for the chest wall, we're going to have to subtract the pleural pressure. You have to ignore the alveolar pressure for a second, but you have to subtract the pleural pressure from the barometric pressure, which, as we already established before, would be 0. So it's literally just the pleural pressure. Now, as for finding the transmittal pressure of the respiratory system as a whole, think of it as the lung and chest wall combined. So you're going to have to subtract the alveolar pressure, but this time from the body surface pressure. You're going to have to ignore the pleural pressure, or you're going to have to consider it as a wall, essentially, that the alveolar pressure is pressing from one side, and the body surface pressure is pressing from the other side. Now, despite needing different methods to measure the transmittal pressure in each part of the respiratory system, when measuring the compliance, the change in volume throughout all the parts are the same, all throughout. Now, this leads into another thing, the reciprocal of the compliance with the parts of the respiratory system. Essentially, if you have, they add up to each other. So if you have two parts, you can find the third. So if you have the reciprocal of the respiratory system, you can subtract either the lung or chest wall to find the other. And if you have the lung or chest wall, you can add them up to find the reciprocal of the respiratory system. Here is the compliance of the respiratory system, and as you can observe, the graph is steepest near the functional residual capacity, which is 3. This means that its compliance is highest at the functional residual capacity, with its compliance decreasing as you go both further up as well as lower down. So the closer you are to the total lung capacity, or 6, or the closer you get to residual volumes, or 1.5, the compliance will decrease and decrease. Why? This is because functional residual capacity is the range that we normally breathe at. This gives the respiratory system a sort of recoil property where it essentially, the further it gets from the functional residual capacity, the more it will recoil back to this range. Now, you can know one thing. The process of inhalation, where we move from functional residual capacity and increase the volume, is a process that takes energy. Why? Because we're moving away from where the compliance is highest. Meanwhile, exhalation, a process where we go from higher volumes towards the functional residual capacity, is a passive process because we're going from low compliance to high compliance. But forced exhalation, where we go from functional residual capacity to volumes below it, will also require energy. So you'll have to keep that in mind. So here's a question. What is the highest compliance for the respiratory system, the one that we just covered? Now, here is a question. What is the highest compliance of the respiratory system? So what this question is basically asking of us is, at what range is the Does the respiratory system find it easiest to stretch? And as we've been discussing earlier, it will be A, the functional residual capacity. It can't be either B nor C due to the fact that C is too high up, total lung capacity. We don't usually breathe to that range, and residual volume is too low. But functional residual capacity, think of it as like a Goldilocks zone. That is usually the range that we breathe in. As you can observe with the lung, its highest compliance will be at lower volumes. That means as volume increases, the compliance will decrease, its ability to stretch will decrease, meaning that the lung constantly wants to recoil downwards to lower volumes. In fact, its resting volume is 200 milliliters, but why we won't be able to reach that is due to two things. The chest wall, which recoils upwards, as well as the residual volume. Now, here is another question. What is the lowest compliance for the lung? Basically, where does the lung find it hardest to stretch? 100% of total lung capacity would be the answer. As we just said, the lung will always recoil downwards. That means its highest compliance will be at residual volumes. This would be highest compliance. Meanwhile, the chest wall is opposite to the lung with its highest compliance at high volumes, with its resting volume, in fact, above the functional residual capacity. This means that the chest wall will always want to recoil upwards towards a high resting volume. Now, this opposes the lung. Now, if we can see here, when you're trying to inhale, you're going to want to increase your lung volume, but this is being opposed by the lung. So we basically say that the lung is limiting maximal inhalation. Meanwhile, for the chest wall, when you want to exhale, you're going to want to decrease your lung volume, which is where the chest wall's compliance is at its lowest. So we say that chest wall is limiting your maximal exhalation. Now, as for a final question, the resting volume of the lung is below residual volume. See, this is why I was using abbreviations the entire lecture. It's because actual exams use abbreviations. Okay, so it's below residual volume and it can never be reached. Why is that? Due to the outward elastic recoil of chest wall. As we just said, the chest wall limits the maximal exhalation, which is why we can never reach the resting volume of the lung. That's it for today, and thank you.